Get started. Hi everyone, I'm Yufu. I'm final year PhD student from Georgia Tech, and I'm excited to share with you this work I did doing my internship with Adobe. And this project was in collaboration with Shunan, Jane, Victor, and Ryan from Adobe Research, and my advisor, John Stasko. So I want to share a personal story about what motivated this work. About 6 or 7 years ago, I was a sports journalist, and I had written a basketball story, not this exact same one. So I sent the draft to my editor, who edited and published it. So I had a habit to engaging with readers and reading their comments. Then I came across a comment that pointed out a numerical error in my article. It says something like, "You got this number wrong, you're not very professional." Well, that hurt. So I asked my editor to fix it and with the correct value, and that got me reflect on it. First, my editor isn't going to help me with fact-checking these numbers. It's just too tedious for them. Second, authoring this data-driven article is very error-prone. You need to go back and forth from data source to your article and transcribe the numbers into your text. And thirdly, sure, this is basketball. Most people don't care about if a player shoots 34% or 35% from the three-point line. But what if I were writing something more serious, something with higher stakes like climate change, inflation rate, or COVID cases? So those errors could potentially mislead my audience and really damage my credibility as a journalist. Furthermore, for audience, it's even harder for them to audit the information they consume online, which could be dangerous, making them more susceptible to fake news. So we're in our age of data, with a vast amount of public data readily available. So media platforms frequently use data to shape their narratives, whether you are glancing at an ESPN sports analysis, or reading a New York Times article on COVID trends, or just scroll through social media, you've likely come across many claims based on data and statistics. So these are what I call data-driven narrative or data claims. When used effectively, they can boost media credibility, provide objective insight, and inform the public. Their perceived objectivity makes them especially convincing and powerful in shaping argument or driving narratives. However, despite their perceived credibility and persuasiveness, data-driven narrative can themselves become a form of misinformation. There are various causes of data-driven misinformation, from errors and outdated data to fabricated information to misinterpretation of data or claims lacking context. So fact-checking is crucial for maintaining the accuracy and accountability of information, especially for news organizations and governments. And it's a key tool in combating misinformation. But with the rapid rise in information production and sharing, especially with Gen AI now, fact-checkers face overwhelming challenges. Manually verifying everything is just unfeasible. So fact-checkers have turned to computing for help. So automated fact-checking has emerged as a key practice and an important area of research to address these challenges. So it has gained significant attention in data mining, NLP, and AI research communities. Efforts range from curating data set and building models to assess whether a claim is worth checking, to focusing on the fact-checking process itself, predicting if a claim is trustworthy or not. So many systems rely on knowledge bases, checking claims against corpora like Wikipedia, scientific articles, or knowledge graph. However, data claims, the focus of our work, aren't explicitly found in knowledge bases, but come from structured data tables. They are often more complex, involving numerical aggregations, calculations, and a wider range of structured data points. For example, the first claim can be verified using a knowledge graph, but the second claim here requires a data set with categorical and numerical data and calculation sum or proportion. So there are a few existing work pursuing similar goals. However, there are still major limitations and room for improvement. The first direction focuses on improving the accuracy of detection and verification. As a result from existing work demonstrate the accuracy or of verification is not that great. And another direction involves like enhancing the system's ability to handle more complex data claims. So the existing work primarily focuses on claims that are about single values. But in the real world, these claims can be much more diverse, such complexity is reflected in semantics, the data operation needed, and some are even compounded data claims that consist of multiple data facts. The third focus is communication. A current approach falls short in providing effective communication of verdicts and explanations. Like existing work from NLP and AI communities, they often overlook the importance of delivering clear and effective communications to potential stakeholders and making the fact-checking result more transparent and actionable. So we want to explore two research questions. How do we enable out-of-box automated fact-checking for data claims? And how do we effectively represent and communicate the data evidence so the results are more digestible and actionable for multiple stakeholders? So to tackle this problem, we adopted the automated fact-checking framework and modified it to fit data claim fact-checking and communication. So researchers have outlined a framework for automated fact-checking. We start with claim detection. Identifying factual claims in the text, then comes evidence retrieval, gathering relevant data to verify those claims. So this is followed by verdict prediction, where the system assesses the evidence to determine if the claim is true or false. And finally, justification production generates human-readable explanations, enhancing transparency and clarity. So this adapted framework we propose has 6 components. It starts with input data articles. We first need to detect the data claims, then map the data claims to data queries that can help retrieve the pertinent data evidence. Then the pertinent data evidence is then used to computationally determine the veracity of the claim, as well as producing the data evidence presentation. And ultimately, we need to design the end-user interactions to make the result more actionable and practical. Then we develop a proof of concept prototype named Alicia to unify and integrate the components of the framework. So the first 3 components makes up its backend, and the last 3 are included in the interface. So let's take a look at the backend pipeline design. So the first step, distinguish data claims from other textual content, is pretty straightforward. A large language model or a trained classifier can handle that sufficiently. But how do we go from data claims to queries that can retrieve the pertinent data evidence? To explore this, we conducted a formative study. We collected over like 100 real-world data claims from different domains and sources, and semantically coded them to better understand the pattern. So we discovered that the process is quite complex. It involves a diverse array of NLP tasks. Like first, data claims often include more than one data fact, like this example. So we need to decompose compound claims into individual data facts. Next, the contextual information that determines the subspace may be omitted. So we need to infer and supplement key information based on the context. Additionally, core references are commonly used to represent real-world entities. So this involves replacing core references with actual entities and attributes derived from the context. Furthermore, the terms used to describe attributes are often inconsistent and even ambiguous. So this motivates us to provide explicit attributes names to improve the identification accuracy. So this complete singular data fact can then be classified into different types, including rank, trend, value, outlier, association, etc. So based on the different types, these data claims can be transformed into specifications that can query the data and apply corresponding operations. So we follow this table that displays the 10 data fact types and corresponding JSON specifications. Please see the paper for more detail. So the data evidence is subsequently used to programmingly determine the veracity and to be presented as data evidence in the interface. As for the interface, there are two key parts to design. First, we need to focus on data evidence representations. Our main goal here is to ensure the alignment with the original data insight conveyed by the data claim. Second, we aim to facilitate a quicker judgment, which will enhance professionals' productivity and boost adoption by general audience. And third, we aim to enhance viewers' confidence in their assessment. Then we designed the data table and visualization for certain types of data facts. Please see the paper for details. Then we need to design the user interaction. In this case, our hypothetical user group are authors or editors who need to proofread, draft, and ensure that the data claims are accurate. Essentially, the scenarios I introduced at the beginning of my talk. So we want to first facilitate rapid reviewing and correction. Then we want to, since the AI may make incorrect inferences, we need to allow users to supervise, intervene, and correct those errors. Thirdly, we aim to support the use of additional reference data to ensure claims can be verified even when the initial data set is incomplete or not suitable. So we integrate the visual designs and interactions into Alicia's interface. So to demonstrate Alicia's utility, imagine a sports editor named Jordan is tasked with reviewing a written draft to ensure the data accuracy in the article. So Jordan first loads the article into Alicia, then select the reference dataset and runs the system. Alicia will automatically generate a fact-checked result. Jordan can click on the individual sentences to review the data evidence, either in data table or visualization format. After reviewing the data evidence, Jordan can decide whether to accept the system's suggestion for an auto-correction of the sentence. You can also click on Fix All button to auto-fix all the inaccurate data claims. In another scenario, Jordan noticed that the AI failed to detect a filter that is among all the centers. He can manually add this filter, and Alicia will evaluate the claim based on the modification and suggest a new sentence for users to correct. So in cases where a claim is unverifiable through the original reference data, Alicia supports users to adding a new dataset to target fact-checking. To streamline the process, Alicia uses GPT to assign a suitability score based on the attribute names and the specific claim, and then reevaluate the claim. So we evaluate two aspects of Alicia regarding our research questions. First, we assess the performance on the two core steps of our NLP pipeline: data fact classification and fact specification transformation. So we had to create our own ground truth data set, since there aren't many for data claim fact checking, especially that suits our purpose. We generated 400 claims across different fact types using templates. We used GPT to make the paraphrased version to better match real-world language, and we manually check the accuracy for it. The results show that GPT is very capable of classifying these claims into various types given proper definition and examples. And second, it's capable of generating well-formed data fact specifications, allow automated fact-checking systems like Alicia to retrieve the pertinent data evidence. So we envision that with the new model that can generate the structural JSON data, this performance could be better. And next, we conducted a mixed method user study where participants reviewing data claims and determine if they were accurate based on the provided data evidence. We measured the time they spent, the confidence level and preferences, and the accuracy in making decisions. We also want to elicit their qualitative feedback to inform the design of every data evidence. We recruited 20 participants, and they were split into two groups, one using visualization and the other using tables. In the first phase, participants either saw a table or visualization and assessed the accuracy of a data claim. here's a brief demo of them doing the task. So each participant completed like 26 tasks in this phase using the data evidence representation. In the second phase, we asked the participant to use the opposite representation for the same task and compare it to previous phase. So we measure their confidence shift and preferences. So each participant, again, completed 26 tasks in the session. So upon completion, we showed the participant the result and conducted a post-study interview. We asked them questions like what design element helped them to build confidence and fact-checking result. Our findings show that visualization charts are more effective than data tables in reducing the time needed to reviewing most data fact types, and the visualization charts increase participant confidence across all data fact types are generally preferred by them. And the overall accuracy is over 90%. Please see the details in the paper. And finally, I want to share some findings and takeaways from our qualitative feedback. We semantically coded the qualitative feedback and found that visualization inherently offer advantage when fact-checking data claims, especially those involving patterns and distribution across many data points. You can see the paper for details. Based on our result, we recommend several strategies for representing data evidence, like displaying data operations, especially the filters, to make the process clear. And second, make the salient information more visually prominent. And third, present key information first with contextual information available on demand. And lastly, consider providing visual aids to enhance understanding. So we view this work as the first step to addressing misleading data-driven information from HCI perspective. We acknowledge several key limitations in our work as well. And for future work, we can go beyond just factual level and assess and communicate the plausibility of data claims at the reasoning level, which is a much more complex challenge. And for fact-checking complex data claims, we need to handle multiple filters and nuances semantics. For example, real-world claim often involve intricate data operations and varied language like peaking, tanking to describe trend. So this adds complexity in verifying whether these claims are accurate, reflect the data or visualization. So that sums up my talk. Thank you.
So I really think this is super cool work. I was wondering, you got at it a little bit because we have these filters and you kind of inspect it, but how have you thought about people kind of just accepting your recommendations of, oh, that must be, incorrect or correct, and how do you think about people just going through, yeah, just change it without
that's
reflecting?
Why we want to represent the data evidence to make it more clear to the audiences, even the users, they can spot the inaccurate or accurate, even when the AI suggests, oh, this one is accurate. They can spot the why is incorrect or correct.
Awesome. Okay, so we are over time. Speakers will be at